Welcome back to the Sleepy Analyst. If you're here for the first time, you found the right place at exactly the right time. Maybe sleep has felt just slightly out of reach lately, and you're hoping that something bigger than your problems might help carry you away from them for a while. That's what we do here. We take the most extraordinary mysteries in the universe and slow them all the way down, until they become something you can float inside of. Tonight, we're drifting through the Milky Way. Our galaxy. The one carrying you right now, this very second, through space at a speed your body will never feel and your mind can barely hold. A vast spiral of 100 billion suns, rotating slowly in the dark for over 13 billion years. There's nowhere to be. Nothing to finish. Just let the words wash over you like a tide, and let the rest carry you wherever sleep is waiting. If these quiet explorations help you rest, please consider subscribing to the Sleepy Analyst. It helps other tired, curious people find their way here. Let's begin with something that is genuinely difficult to hold in your mind. Not because you're not smart enough, because no human mind is built to hold it. And somehow, that's part of what makes it beautiful. The Milky Way is approximately 100,000 light-years across. A light-year is not a unit of time. It's a unit of distance, the distance that light travels in one full year. Light moves at about 300,000 kilometers per second. In a single second, it can travel 7.5 times around the entire Earth. In a year, it covers roughly 9.5 trillion kilometers. And the Milky Way is 100,000 of those years wide. Try holding that. 100,000 years of light travel, edge to edge. The light leaving one side of our galaxy right now, beginning its journey at this very moment, at 300,000 kilometers per second, will not reach the other side until the year 100,000 has passed. Long after every human language spoken today has been forgotten. Long after the continents have shifted into new configurations. Long after almost everything we recognize about our civilization has dissolved into history. And you live inside it. If you shrank the entire Milky Way down to the size of the continental United States, coast to coast, our solar system, the sun and all its planets, everything we've ever explored directly, would be approximately the size of a single quarter. A small coin, sitting somewhere in the middle of a continent made of starlight. That is how large the galaxy is relative to everything we've ever touched. And that's just the visible part. Here is something you can carry with you from tonight forever, and think about on any ordinary day when the world feels too small or too slow. You are never still. Right now, while you rest, while your eyes grow heavy and your breathing slows, the solar system is hurtling through space at more than 828,000 kilometers per hour. That's roughly 230 kilometers every single second. The Earth is moving. The sun is moving. This room, this bed, every atom of your body, all of it is sweeping forward through the galaxy in a vast, silent arc. And yet, you feel nothing. There's no wind. No vibration. No sensation of speed whatsoever. Because space is so vast, and the force is so steady, that the greatest journey you will ever take happens in complete, absolute silence. Even at that staggering speed, it takes approximately 225 million years to complete just one full orbit around the Milky Way. Astronomers call this period a galactic year. In the 4.5 billion years that Earth has existed, we have completed only about 20 of these orbits. 20 slow, silent laps around the galaxy. The last time Earth was in roughly the same position it occupies tonight, the very first dinosaurs were just beginning to walk. The continents were arranged entirely differently. The oceans sat in different places. The air itself had a different composition. It was a world we would not recognize as home. And in another 225 million years, when Earth completes its next lap, whatever exists here may be just as unimaginable to us now as we would be to those first dinosaurs then. Everything is in motion. Always. Quietly. Endlessly. Even as you sleep. If you could somehow leave the Milky Way, accelerate outward at impossible speed until you were 1,000,000 light-years away, and then turn to look back, what would you see? A flattened disk of light, glowing softly against the absolute black of intergalactic space. A luminous, concentrated center, the core of the galaxy, bright with the combined light of billions of densely packed stars. And from that center, curving outward like the arms of a pinwheel, the great spiral arms of the galaxy winding gracefully into the dark. It would be one of the most beautiful things any human eye has ever seen. A slow, radiant whirlpool made entirely of starlight, rotating in silence, thousands of light-years across. But here is the strange and humbling truth: we have never actually seen the Milky Way from this perspective. Every stunning spiral galaxy image you've ever admired, those gorgeous images of arms curving through space, those are other galaxies. M31, the Andromeda Galaxy. M101, the Pinwheel Galaxy. The Whirlpool. The Sombrero. We live inside the Milky Way. We are embedded in its disk, roughly 26,000 light-years from the center, in a relatively quiet region called the Orion Spur. And because we're inside it, we cannot step back and photograph it the way we photograph other galaxies. When we look at the night sky, we're looking from the inside outward and inward. The faint, hazy river of light that crosses a dark sky on a clear night, the Milky Way as we see it, is simply the view along the plane of the disk. Thousands of light-years of stars, their combined light creating that soft, luminous band. We stand in a forest and look along the line of the trees. We cannot see the shape of the forest from within. We can only see the vastness that surrounds us. It took centuries of observation, mathematical reasoning, and the development of radio and infrared telescopes before we could even approximate a map of our own home. In some ways, that's a beautiful metaphor for the nature of home itself. We are often the last to see the shape of the place we've always been. Now here is one of the strangest facts about the galaxy you call home. Most of it is invisible. Not in a poetic sense. Not because it's too far away or too faint. The majority of the Milky Way's mass simply does not emit any light, reflect any light, or interact with light in any way we can detect. Scientists call it dark matter. And its existence was uncovered through a puzzle. When astronomers began carefully measuring how quickly stars orbit the center of the galaxy at different distances, they found something that shouldn't be possible. Stars out near the edges of the galactic disk, stars far from the concentrated mass of the core, were orbiting nearly as fast as stars much closer to the center. Sometimes just as fast. By the laws of gravity, that shouldn't happen. If the only mass in the galaxy were what we can see, the stars, the gas, the dust, then the outer stars would be orbiting far too quickly. They should be flung outward, scattered into space like water drops from a spinning wheel. And yet they remain. Perfectly, stubbornly in orbit. Something invisible is holding them in place. Something massive, extending far beyond the visible disk of the galaxy in a vast spherical halo. Something that outweighs all the visible matter in the Milky Way many times over. That something is dark matter. And despite decades of sophisticated experiments, detectors buried deep underground to shield them from ordinary cosmic radiation, detectors orbiting in space, particle accelerators attempting to produce dark matter particles, we have never directly detected it. We don't know what it is. We only know what it does. It bends light around it through gravity. It shapes the structure of galaxies. It holds the Milky Way together. The galaxy you live in, the one carrying you silently through space right now, is held together by something we cannot see, cannot touch, and cannot yet name. There's something strangely restful about that. The universe has its mysteries. And that's all right. We rest inside questions as vast as the galaxy itself. At the very center of the Milky Way, hidden behind thick walls of gas and dust that block every wavelength of visible light, something extraordinary exists. A black hole. Not just any black hole. A supermassive black hole, more than 4 million times the mass of our Sun, compressed into a region of space smaller than the orbit of Mercury. We call it Sagittarius A star. We cannot photograph it directly in visible light. The dust between us and the galactic center is simply too dense, too layered. But we can watch the stars that orbit near it. And those stars do something that should stop you in your tracks. They whip around the central point at tremendous speeds, tracing tight, looping paths around something we cannot see, something invisible that nonetheless exerts the gravitational force of 4 million suns. Some of the nearest stars orbit so close and so fast that they complete a full revolution in just a few years. Astronomers have watched individual stars complete entire orbits within the span of a human career. The motion of those stars is our proof. A mass 4 million times greater than the Sun, occupying a space smaller than the distance from Earth to Venus. A point of gravity so extreme that nothing, not matter, not light, can escape it once it crosses the threshold. For now, Sagittarius A star is quiet. Astronomers call it quiescent, at rest. Occasionally, a cloud of gas drifts too close and flares with X-rays as material accelerates into the event horizon. But compared to what it once may have been, it sleeps. Because there is evidence, strange, powerful evidence, that long ago, this black hole woke up. Stretching tens of thousands of light-years above and below the center of our galaxy are two enormous structures. Enormous ghostly lobes of high-energy radiation, specifically gamma rays, billowing outward from the galactic core like two vast, invisible balloons inflated from within. They are called the Fermi bubbles. They were discovered in 2010, and they immediately raised a question that scientists are still working to answer fully: what created them? Each bubble stretches roughly 25,000 light-years from top to bottom. Together, they are larger than the visible disk of the Milky Way itself. They are invisible to human eyes in ordinary light, but in gamma-ray wavelengths, they are colossal. One possibility is an ancient burst of star formation near the galactic center, a period millions of years ago when stars formed rapidly, lived briefly, and exploded in enormous numbers, their combined shockwaves carving these lobes into the halo above and below. The other possibility is more dramatic. There is evidence that Sagittarius A star may have once burned as a quasar. Quasars are the blazing, active cores of other galaxies, supermassive black holes consuming enormous quantities of matter at astonishing rates, releasing energy that outshines the combined light of hundreds of billions of stars. They are among the most luminous objects in the known universe. Some quasars are visible from halfway across the observable cosmos. If the Milky Way's own black hole once burned like this, if it fed and blazed and roared, our galaxy would have looked completely different. Not a quiet, darkened spiral, but a brilliant, radiant structure wrapped around a blinding heart of light. Visible to any civilization with eyes, from millions of light-years in every direction. That era has passed. The black hole has quieted. The spiral arms have settled into their current calm rotation. But the Fermi bubbles remain, slow, fading echoes of ancient violence, drifting silently above and below the stars we know. Monuments to a time when the Milky Way was something else entirely. When astronomers began systematically mapping the central regions of the Milky Way in infrared light, the kind that penetrates through dust clouds where visible light cannot, they expected to find a smooth, roughly spherical bulge of old stars at the core. What they found instead was considerably stranger. The central bulge is shaped like a peanut. Seen from the side, it swells in the middle and narrows toward the ends, forming something closer to a three-dimensional X-shape or a twisted hourglass made entirely of billions of stars. And cutting across the center of the galaxy, from one side to the other, is a dense, elongated bar of stars, a glowing bridge of stellar material rotating slowly around the core. This bar is not decorative. It is a gravitationally significant structure that shapes the inner spiral arms, funnels gas inward toward the black hole at the center, and drives star formation in its vicinity. Bars like this appear in roughly 2/3 of all spiral galaxies we observe, suggesting they are a natural stage in galactic evolution. And within that bar, astronomers have found hints of something even more surprising, a smaller inner bar, tilted at a different angle and rotating at a different rate, nested inside the larger structure like a galaxy within a galaxy. The center of the Milky Way is not a single simple point. It is a layered, shifting labyrinth of light and gravity, intricate and complex far beyond what any early diagram or textbook ever suggested. And at the very heart of all of it, for million solar masses of compressed gravity sleeps in the dark. There is something else threading through the Milky Way that is easy to forget because it produces no light and makes no sound. A magnetic field. The Milky Way is laced with a vast, galaxy-spanning magnetic field. It extends across the disk, rises into the halo above and below the plane of stars, and weaves through the clouds of gas between them. By earthly standards, it is incredibly weak, far too faint to affect a compass, too diffuse to measure without specialized instruments. But over galactic distances, across thousands of light-years, it shapes how cosmic rays travel through space, how gas clouds collapse and form new stars, how material flows through the interstellar medium. It aligns with the spiral arms. It forms arcs above the galactic plane. It twists into loops in ways that still challenge theorists to explain. To study it, astronomers use radio telescopes to detect how the field polarizes the light from distant stars, how it subtly rotates the orientation of light waves as they pass through magnetized regions of space. Slowly, painstakingly, a picture of the galaxy's magnetic architecture has emerged. The Milky Way does not just glow with light. It breathes with magnetism, a subtle, invisible pulse running through the bones of the galaxy. An electromagnetic skeleton beneath the stars. Somewhere in the Milky Way right now, in an enormous cold cloud of molecular hydrogen drifting through one of the spiral arms, something is beginning. There is no light yet. No heat. No sound, of course. Just darkness, and cold, and an almost imperceptible increase in density in one small region of the cloud, a subtle gathering of atoms drawn together by the same force that holds you to the Earth. Gravity. Over tens of thousands of years, so slowly that any individual human life would capture only the tiniest fraction of the process, that slightly denser region draws more and more gas toward it. The cloud begins to collapse. As it falls inward, it heats. It spins. The collapse naturally flattens into a disk, angular momentum conserved, physics doing what physics always does, with a bright, hot, increasingly dense core at the center. The temperature climbs. 1,000 degrees. 10,000. 100,000. 1,000,000. The pressure builds to extremes we have no earthly experience of. And then, at approximately 10 million degrees Kelvin, hydrogen atoms moving fast enough and packed close enough begin to fuse. Protons overcome their electromagnetic repulsion, merge, and in that merger, release energy. Nuclear fusion ignites. A star is born. From the coldest, darkest shadows in the galaxy come the brightest lights in the universe. All of them. Every one. Spun gently into being by the quiet, patient force of gravity working on lonely wisps of gas. Every star you have ever seen in the night sky began this way. Including our sun. Including the distant lights you're imagining right now as you drift. The spiral arms of the Milky Way are not simply made of stars. They are woven, more accurately, from the birthplaces of stars. Enormous molecular clouds, sometimes hundreds of light-years across, containing enough gas to form millions of suns, drift slowly through the galaxy. When these clouds encounter a density wave moving through a spiral arm, they are compressed. Regions of higher density trigger collapse. Dozens, hundreds, sometimes thousands of stars ignite in the same general area over a span of millions of years. These regions are called stellar nurseries. They are simultaneously chaotic and beautiful. Intense ultraviolet radiation from the hottest newborn stars ionizes the surrounding gas, making it glow in extraordinary colors: the pale blue of ionized oxygen, the deep rose pink of hydrogen gas excited by radiation, the soft green of ionized sulfur. Pillars of dense gas resist the erosion of stellar winds, creating the famous column-shaped structures astronomers poetically call elephant trunks, fingers of gas and dust where new stars are forming even as the pillars themselves are slowly destroyed. The great nebulae visible through even modest telescopes, the Orion Nebula, the Eagle Nebula with its pillars of creation, the vast Carina Nebula, are all stellar nurseries at various stages. Cradles of creation, active right now. New stars are forming in them at this very moment. As you rest, as the world outside is quiet, somewhere in the Milky Way, a star is igniting for the first time, a new sun, surrounded by a disk of material that may eventually become planets, beginning a life that will last millions or billions of years. Stars live long lives by any human measure. But they do not live forever. And the way a star dies depends almost entirely on how massive it was when it began. A star like our Sun, a middleweight, middle-aged, thoroughly ordinary star, will spend most of its life fusing hydrogen into helium in its core. This process, which has been going on in the Sun for about 4.5 billion years, will continue for approximately another 5 billion years. A long, stable, productive life. Eventually, when the hydrogen in the core runs out, the Sun will expand. It will swell into a red giant, growing large enough to engulf the inner planets, potentially including Earth, as the outer layers puff outward while the core contracts. For a time it will be larger than 100 suns. But the end, for a star like the Sun, is not violent. Over hundreds of thousands of years, the outer layers drift gently into space, forming a luminous, slowly expanding cloud called a planetary nebula, one of the most beautiful structures in the galaxy, despite the misleading name. These glowing shells of gas come in extraordinary shapes: rings, hourglasses, butterflies, spheres. What remains at the center is a white dwarf, the compressed, cooling core of the former star. Roughly the size of Earth, but with the mass of the Sun. So dense that a teaspoon of its material would weigh several tons on Earth's surface. It glows from residual heat, slowly cooling over billions of years, carrying forward the memory of a star that once burned. For more massive stars, those with several times or more the mass of the Sun, the ending is entirely different. These stars live faster, burn hotter, and die violently. When the fuel in the core runs out, the collapse is so rapid, so extreme, that it cannot be arrested by the same processes that stop lighter stars. In less than a second, the core implodes. The conditions reach unimaginable extremes, densities greater than an atomic nucleus, temperatures in the billions of degrees. The collapse rebounds. A shockwave blasts outward through the star. And in an explosion that can briefly outshine an entire galaxy of hundreds of billions of stars, the outer layers of the star are flung into space. This is a supernova, one of the most energetic events in the known universe. And it is profoundly generous. Everything that star spent its life creating, carbon forged from helium, oxygen built from carbon, silicon built from oxygen, iron assembled in the final collapse, all of it is hurled outward into the surrounding space. It mixes with the interstellar medium, cools over thousands of years, eventually condenses into new clouds, new stars, new planets. The iron in your blood was made in a star and scattered by a supernova. The calcium in your bones, the oxygen in your lungs, the carbon that forms the backbone of every molecule in your body. All of it was processed inside stars and delivered to the galaxy by their deaths. You are, in the most literal chemical sense, a child of stellar violence. When a massive star collapses and explodes, what remains depends on the mass of the original star. In many cases, the remnant is a neutron star. A neutron star is one of the most extreme objects in the universe short of a black hole. It contains more mass than our Sun, sometimes much more, compressed into a sphere perhaps 20 kilometers across. The size of a city. A teaspoon of neutron star material would weigh more than 1 billion tons on Earth. The gravity at its surface is approximately 200 billion times stronger than the gravity you feel right now. Some neutron stars are left spinning rapidly after the explosion that created them, spun up by the conservation of angular momentum, like a figure skater pulling in their arms. As they spin, beams of radio waves and other radiation sweep from their poles like cosmic lighthouses, sweeping through space with each rotation. From Earth, we detect these sweeping beams as regular, precise pulses of radio waves. We call them pulsars. Some rotate several hundred times per second. And they maintain that rotation with extraordinary, almost uncanny regularity, keeping time more accurately, in some cases, than the atomic clocks we use to coordinate global communications. When two neutron stars happen to orbit each other in a binary system, and they do exist in such pairs, they slowly spiral inward, radiating energy as gravitational waves, until they finally collide. The event is called a kilonova. And in the brief, blinding brilliance of that collision, in fractions of a second, conditions are created that are extreme enough to forge elements that no star can produce alone. Gold, platinum, uranium, iridium. The heaviest, rarest elements. The gold in any piece of jewelry you own. The platinum in any catalyst. These are not products of ordinary stellar burning. Conditions in ordinary stars are simply not extreme enough to create them in significant quantities. They are born in the moment of neutron-star collision, scattered into a cloud, incorporated into a forming solar system, and found their way here across billions of years. The galaxy is an alchemist. Patient, methodical, working across timescales that make human history feel like a single held breath. The Milky Way has a beautiful, peaceful appearance from a distance. A slow, graceful spiral rotating in the dark. Ancient and steady. But it is not, and has never been, peaceful. Our galaxy is a conqueror. Over billions of years, it has drawn smaller galaxies toward itself, disrupted them, dismantled them, and absorbed them, star by star, stream by stream, until those smaller galaxies ceased to exist as independent entities, their material folded into the Milky Way's halo and disk. One galaxy, the Sagittarius dwarf spheroidal galaxy, is being pulled apart right now. It has orbited the Milky Way several times already, each pass closer and more destructive than the last. With every orbit, tidal forces strip away more of its stars, stretching them into long, looping streams that wrap around our disk like faint ribbons of stolen light. Astronomers have identified dozens of these events by tracing stellar streams across the sky and analyzing the chemical compositions and orbital motions of halo stars. One particularly large ancient merger, called the Gaia-Enceladus event, occurred perhaps 8 to 10 billion years ago and may have contributed an enormous number of stars to the inner halo, possibly reshaping the early structure of the disk. The Milky Way is not a pristine, unaltered spiral. It is a composite, built across billions of years from quiet collisions, stitched together from the remains of dozens of smaller worlds. Like most things of great beauty, it carries in its structure the unmistakable record of its own complicated history. If you could map every star in the Milky Way's halo, not just their positions, but their velocities, their ages, their chemical compositions, you would find something extraordinary hidden in what looks at first like random scatter. Thin ribbons of stars. Long arcs and curves, barely visible individually, but unmistakable when revealed by careful mapping. Stars that share the same trajectory, the same age, the same chemical fingerprint, traveling together through the halo not by coincidence, but because they were born together in a galaxy that no longer exists. These are stellar streams. The remnants of smaller galaxies that wandered too close to the Milky Way and were gradually pulled apart by tidal forces. As these smaller systems orbit, the gravitational difference between the near and far sides of the orbiting galaxy, the tidal gradient, slowly stretches it into a long line, smearing its stars along the former orbital path over hundreds of millions of years. The Sagittarius stream wraps around the Milky Way in a vast ring. The Orphan stream traces a long, mysterious arc with no clearly identified parent galaxy. The Monoceros ring, a faint structure encircling the outer disk, may be the remnant of another absorbed companion. When astronomers map these streams, they are reading the Milky Way's autobiography, a record of ancient encounters, consumed companions, and slow gravitational unraveling, written in the distribution of stars across the sky. The galaxy keeps its history in its motion. Most stars drift calmly through the galaxy. Their orbits are stable, steady, following the slow swirl of the disk over hundreds of millions of years without incident. But occasionally, rarely, but definitively, a star is flung outward with astonishing violence. When a binary star system, two stars orbiting each other, drifts too close to the supermassive black hole at the galactic center, something catastrophic happens. The black hole's gravity disrupts the pair. One star falls toward the event horizon, captured. The other is catapulted outward, slingshot by the interaction, launched at speeds exceeding 1,000,000 kilometers per hour. At that velocity, it is traveling faster than the escape velocity of the Milky Way itself. It will not stop. It will not be captured by another star's gravity. It will not return. These are called hypervelocity stars. They travel alone, far from the galactic plane, speeding outward through absolute emptiness into intergalactic space. The galaxy grows smaller behind them. The next galaxy, millions of light-years away, grows slowly, imperceptibly larger ahead. They are the loneliest objects in the galaxy. Each one a tiny wandering light carrying the memory of the Milky Way outward into the permanent dark between galaxies. Solitary pilgrims, never to find a home again. The mechanism that creates hypervelocity stars, the gravitational slingshot of a binary system disrupted by a supermassive black hole, is called the Hills mechanism, named after astrophysicist Jack Hills, who predicted it in 1988. The first confirmed hypervelocity star was discovered in 2005. Since then, dozens more have been identified. Some are traveling at 2 million kilometers per hour. A few may be traveling even faster. Not all hypervelocity stars come from the galactic center. Some may be launched by other mechanisms, the asymmetric explosion of a supernova in a binary system, for example, where the recoil kicks the surviving companion star to tremendous velocity. Or three-body gravitational interactions in dense stellar regions, where the energy exchange between three stars can accelerate one of them to escape velocity. The result in each case is the same: the star that once belonged to the galaxy, now irreversibly bound for intergalactic exile. There is something quietly poignant about it. Even in a galaxy held together by gravity, a structure that has persisted for 13 billion years, there are moments of release. Moments when a star breaks free of everything and goes. High above the horizon on a clear autumn night in the northern hemisphere, if you know exactly where to look, you can see it with the naked eye. A faint, softly glowing oval. Easy to mistake for a nearby nebula or a particularly diffuse star cluster. That glow is the combined light of approximately 1 trillion stars. It is the Andromeda Galaxy, catalogued as Messier 31, a spiral galaxy much like our own, lying approximately 2.5 million light-years away. The most distant object visible to the unaided human eye. And it is moving steadily toward us. In approximately 4.5 billion years, a time span that contains the entire current age of the Earth repeated, and then repeated again, the Milky Way and Andromeda will collide. The collision has been confirmed. Multiple independent measurements of Andromeda's position and velocity leave little doubt. The two galaxies are approaching each other at roughly 110 kilometers per second, with a trajectory that will bring them into contact. But it won't be the kind of collision you might imagine. Despite each galaxy containing hundreds of billions of stars, the stars themselves are so small relative to the vast distances between them that virtually none will actually physically collide. The space between stars within a galaxy is so enormous that the two galaxies can pass through each other like two swarms of fireflies merging in the dark, interleaving, not impacting. What will be profoundly disrupted is the shape of both galaxies. The gravity of all those stars will distort both structures dramatically. Long tidal tails of stars will be flung outward into intergalactic space. The grand spiral arms of both galaxies will be torn apart. The two supermassive black holes, one from each galaxy, will spiral toward each other, gradually, over billions of years. After multiple passes, each bringing the two galaxies into closer and more permanent merger, they will eventually combine into a single, larger galaxy. No longer spiral in shape, but a great, featureless elliptical, a vast, glowing ball of stars. Some astronomers have already given it a name, Milkymeda. Our Sun will almost certainly survive. It will be pushed into a different orbit within the new galaxy, its neighborhood transformed almost beyond recognition. And the night sky, if there are eyes to see it, will have become something entirely new, a galaxy-wide display of restructured starlight, different from anything that has ever existed. Even galaxies are not eternal. They evolve, collide, and begin again. There is a common image of space as pure, featureless emptiness. A vast, cold vacuum between the stars, with nothing in it, no substance, no structure, no activity whatsoever. That image is profoundly misleading. The space between stars is called the interstellar medium. And it is anything but empty. It is a constantly shifting, endlessly complex blend of gas, dust, plasma, magnetic fields, and energy that permeates the entire galaxy like an invisible atmosphere. In some places, the interstellar medium forms vast, cold molecular clouds, dense enough to block starlight completely, cold enough to allow complex molecules to form on the surfaces of dust grains. These are the stellar nurseries we spoke of earlier, the darkest regions giving rise to the brightest objects. In other places, it is hot and diffuse, thin plasma heated to millions of degrees by the shock waves of ancient supernovas, glowing faintly in X-rays but nearly invisible in ordinary light. Between these extremes lies a complex continuum, warm neutral gas filling vast bubbles carved by stellar winds, cool atomic hydrogen stretched across the disk in diffuse sheets, filamentary structures threading through the halo like tendrils of smoke, shockwave fronts rippling outward from stellar explosions, compressing gas into new regions of density. On large scales, this creates a kind of turbulence, a slow motion, enormous, perpetually shifting sea of matter and energy filling the spaces between stars. The quiet fabric from which galaxies evolve. The raw material from which all stars form. What looks from afar like calm, dark emptiness is, up close, one of the most dynamic and complex environments in the universe. The dark is alive. Right now, while you rest, trillions of tiny particles are passing through your body. Not metaphorically. Physically. Through your skin, through your organs, through your bones, through the mattress beneath you, through the floor, through the Earth's crust, through the entire planet, and out the other side, as if none of it were there at all. These are called neutrinos. They are among the most abundant particles in the universe, produced in enormous quantities by nuclear reactions, in the Sun, in supernovas, in the collisions of cosmic rays with atoms in Earth's atmosphere. Every second, the Sun alone fires approximately 65 billion neutrinos through every square centimeter of your skin. They are almost massless. They carry no electric charge. They interact with ordinary matter so weakly, so vanishingly rarely, that they can pass through a light year of solid lead and almost certainly emerge without a single interaction. The Milky Way is absolutely saturated with neutrinos. Billions of years of stellar activity have filled the galaxy with these ghostly particles. They stream through everything, carrying information from places we cannot see directly, from the cores of stars where no light can escape, from the violent final moments of stellar collapse, from ancient events we cannot observe by any other means. Catching even a handful requires extraordinary effort. Detectors buried kilometers deep underground, shielded from ordinary cosmic noise by millions of tons of rock, watch for the rare flashes of light produced when a neutrino happens to interact with a particle of water or ice. The IceCube Neutrino Observatory at the South Pole has instrumented a cubic kilometer of Antarctic ice for exactly this purpose. Even as you rest, the galaxy is whispering in particles. In silence. In lightless rays that pass through you without asking permission, carrying stories from the distant fires of the Milky Way. Neutrinos are not the only things passing through you from the galaxy. High-energy particles, mostly protons and atomic nuclei, sometimes electrons, occasionally heavier nuclei, are constantly streaming through space at nearly the speed of light. They were launched, most of them, by supernovas and other violent astrophysical events across the galaxy. Some from outside the galaxy entirely. These are cosmic rays. And they are everywhere. When they reach Earth, most are stopped by the atmosphere, but not before producing showers of secondary particles that cascade downward, reaching the ground. At sea level, roughly one cosmic ray particle passes through every square centimeter of your body every minute. In a room this size, thousands of cosmic ray particles are streaming through the space around you every second. They travel through the galaxy's magnetic field, bending and spiraling, bouncing off clouds, losing their directional information over distances. By the time they arrive at Earth, we cannot directly trace them back to their source. Each one is an anonymous message, a particle traveling for millions of years from an explosion we cannot identify, delivering its tiny payload of kinetic energy to the first solid thing it encounters. The galaxy speaks in particles. In energy. In all kinds of radiation that human eyes cannot see and human skin cannot feel. But they are there, ceaselessly, carrying the Milky Way's ongoing story across the void to every corner of the disk. Among the most haunting objects in the galaxy are the ones we cannot see. Planets that have no sun. Some of these rogue planets formed normally, coalescing from the disk of gas and dust surrounding a young star in the usual way. But through gravitational interactions with other planets in the forming solar system, they were ejected before they could settle into stable orbits. Flung outward by a close encounter, they achieved escape velocity and departed, leaving their star behind forever. Others may never have belonged to any star at all, having formed directly from collapsing gas clouds too small and diffuse to ignite fusion, wandering free since the earliest days of their existence. They drift through the galaxy in complete darkness. No sunrise. No seasons. No warmth from any star in any direction. Their surfaces, if they have solid surfaces, exist in permanent, absolute night. They are warmed only by faint internal heat generated by the slow settling of their own mass during formation, gradually cooling over billions of years. Current estimates suggest there may be billions of these worlds drifting through the Milky Way. Perhaps more rogue planets than there are stars. An entire shadow population of lightless, nameless worlds, invisible to our telescopes, following long, cold paths through the spaces between stars. For every star you see in the night sky, there may be multiple worlds drifting silently in the dark around it, or between the stars themselves, and we would never know they were there. The galaxy is larger in its invisible parts than in its visible ones. Here is an image worth holding as you drift towards sleep tonight. The galaxy breathes. Through a process astronomers call the galactic fountain, gas moves in a slow, vast cycle between the disk and the halo above and below it. When clusters of massive stars form and live their brief, brilliant lives, when the most massive among them explode as supernovas, the energy from those explosions drives hot gas upward. It punches through the disk of the galaxy and vents into the halo above and below, rising in enormous columns of heated, enriched material. Up in the halo, far from the plane of stars, the gas cools. The heavy elements forged in those dead stars, carbon, oxygen, iron, mix into it slowly. Over millions of years, the enriched gas condenses. And it rains back down. Gently, slowly, across the disk of the galaxy, settling back into the interstellar medium from which new stars and planets eventually form. The galaxy inhales. It processes. It exhales. It circulates, the way a great living system circulates the materials it needs, the way a tide draws in and releases, the way a breath rises and falls. You are resting in the belly of something that breathes. Slowly. Patient. Over timescales our calendars cannot begin to contain. Not every star in the Milky Way was born here. In the outer halo, that vast, diffuse spherical region surrounding the disk, there are stars drifting in long, slow orbits that appear to be older than the galaxy itself. Not older than the universe, but older than the Milky Way as we know it, older than the disk, older than the spiral structure, older than what we would recognize as our home galaxy. How is that possible? The answer lies in the Milky Way's violent past. Before the galaxy had fully assembled its current form, before the disk had settled and the spiral arms had taken shape, smaller, earlier galaxies existed in the same region of space. When those ancient galaxies merged with the proto-Milky Way billions of years ago, their stars were incorporated into the halo. And so in the halo today, drifting in tilted, looping orbits that don't quite fit the disk's rotation, are stars that formed before the Milky Way was the Milky Way. Stars born in galaxies that no longer exist as separate entities. Wanderers from a time when the universe was younger, wilder, and still learning to organize itself into the structures we see today. They move slowly through the outer halo, far above the galactic plane, like elder spirits from a time before spirals. Their light carries the chemical memory of an era we cannot otherwise access. Hypermetal poor stars, fossils of the dawn. Among the rarest and most scientifically precious objects in the Milky Way are the stars astronomers call hypermetal poor. In astronomy, metals refers to any element heavier than helium, everything from carbon and oxygen to iron and gold. The earliest stars in the universe had almost no metals at all, because they formed before any previous generation of stars had lived and died and scattered heavier elements into space. They burned on pure hydrogen and helium, the only elements produced in significant quantities by the Big Bang. Some of the most extreme hypermetal-poor stars found in the Milky Way's halo contain less than 1/10,000th of the iron found in our Sun. Their atmospheres are almost perfectly pristine, nearly identical to the composition of the early universe itself. These stars are believed to have formed within the first few 100 million years after the Big Bang, perhaps from clouds enriched by the very first generation of supernova explosions. They are still here. Still burning, slowly, dimly, with a soft red glow, low in mass and long-lived. Each one a time capsule. A living relic from the dawn of cosmic history, drifting quietly in the outer halo, preserving in its chemical composition a snapshot of conditions that no longer exist anywhere in the observable universe. They are fossils made of light. Every star in the Milky Way carries a unique chemical signature. By capturing a star's light and breaking it into its component wavelengths, a process called spectroscopy, astronomers can determine exactly what elements are present in the star's atmosphere, and in what proportions. The result is a chemical biography. Not just what the star is made of, but where it came from, when it formed, and what came before it. A star rich in heavy elements, iron, nickel, calcium, strontium, formed in a region where previous generations of stars had already lived and died, enriching the surrounding gas through their supernova. A star poor in heavy elements formed earlier, or in a region where fewer enrichment events had occurred. By comparing the chemical fingerprints of thousands of stars across the halo, the disk, and the inner bulge, astronomers can trace the history of star formation across the entire galaxy, identifying which stars were born together, which came from absorbed smaller galaxies, which are genuinely ancient, and which are surprisingly young. Chemistry becomes a kind of time machine. Each star a page in a very old book. Written in light, and patient enough to wait billions of years for someone to read it. One of the most fundamental challenges in studying the Milky Way, and the broader universe, is the question of distance. How do you measure how far away something is when you cannot travel to it? When you cannot bounce a signal off it and measure the return time? When all you have is the light arriving at your telescope? For nearby stars, geometry works beautifully. As Earth orbits the Sun, nearby stars appear to shift slightly in position against the background of more distant stars, a phenomenon called parallax. By measuring that shift over 6 months, astronomers can triangulate the distance with great precision. But parallax only works for relatively nearby stars. For distances of thousands of light-years, the shifts become too tiny to measure reliably. This is where a special class of star became one of the most important tools in all of astronomy. In the early 20th century, astronomer Henrietta Swan Leavitt, working at Harvard Observatory, in a time when women at such institutions were employed to perform calculations and often denied credit for their discoveries, identified a relationship of extraordinary power. She noticed that certain pulsating stars called Cepheid variables, stars that regularly brighten and dim as they expand and contract, showed a consistent, repeatable relationship between how long they took to complete one pulsation cycle and how intrinsically bright they actually were. The longer the period, the more luminous the star. This meant that by simply measuring how long a Cepheid variable takes to pulse, you could calculate its true luminosity, how bright it actually is, regardless of distance. And by comparing that true luminosity to how bright it appears in the sky, you could calculate exactly how far away it must be. These pulsating stars became known as standard candles. They allowed astronomers to measure distances across the galaxy and then beyond, ultimately revealing that the fuzzy smudges in early telescopes were not clouds within our galaxy but entirely separate galaxies, millions of light-years away. Leavitt's discovery cracked open the scale of the cosmos. They are lights that measure the dark. Blinking beacons scattered through the spiral, letting us chart the galaxy from within, the way a lighthouse measures the distance of the sea. For most of human history, we mapped the Milky Way one careful observation at a time, one telescope, one star, one measurement at a time, slowly building a picture across centuries of patient work. In December 2013, the European Space Agency launched a spacecraft called Gaia. Its mission was unlike anything attempted before, to measure the precise position, velocity, color, and brightness of over 2 billion stars simultaneously. 2 billion individual stars. Each one measured not once, but repeatedly over years. Gaia sweeps the sky constantly, building up an increasingly precise picture of the galaxy's three-dimensional structure and its motion through time. With each new release of Gaia data, and there have been several, each more detailed than the last, the picture of our galaxy becomes sharper, stranger, and richer. Streams from ancient galactic mergers emerge from what previously looked like random scatter. The warp of the outer disk is mapped with unprecedented precision. The Sun's orbit around the galaxy is traced with extraordinary detail. Candidate siblings of the Sun, stars that may have formed from the same cloud billions of years ago, are identified and catalogued. It is, quietly and without fanfare, one of the most significant scientific instruments ever built. A patient, methodical revolution in our understanding of the galaxy we live in, turning what was once a hazy smear of undifferentiated starlight into a sharp, living, three-dimensional map. And it is still working. Still measuring. Still sending data back. The Milky Way, for all its grandeur, 100 billion stars, a dark matter halo extending far beyond the visible disk, a history stretching back nearly to the beginning of time, is not alone. It belongs to a community. A collection of more than 50 galaxies, gravitationally bound to each other, drifting together through the larger universe. Astronomers call this the local group. It spans more than 10 million light-years, a vast region of space by any human scale, and yet it is tiny compared to the larger structures of the cosmos. Most of the local group's members are small, faint dwarf galaxies, irregular in shape, poor in stars, many composed almost entirely of dark matter with only a thin scattering of luminous material. They orbit the two giant spirals that dominate the group, the Milky Way and Andromeda. Each of the two great spirals has its own retinue of satellites, smaller galaxies bound in orbit, some being gradually consumed, some on their first approach. The large and small Magellanic Clouds orbit the Milky Way. The Triangulum Galaxy, M33, visible to the naked eye on very dark nights, orbits Andromeda. Despite the vast separations between them, these galaxies are not drifting apart. Most are moving slowly toward one another, held together by the web of shared gravity. We are part of a family, quiet, widely spaced, but still linked by the invisible threads of mutual attraction. Visible from the southern hemisphere of Earth, two irregular galaxies hover near the Milky Way, glowing softly against the night sky. The large Magellanic Cloud and the small Magellanic Cloud. To the naked eye, they look like detached pieces of the Milky Way, faint, cloud-like patches of concentrated starlight. For many years, astronomers assumed these were longtime companions, satellite galaxies that had been orbiting the Milky Way for billions of years, slowly being absorbed, bound to us in a gravitational partnership extending deep into the galaxy's past. But new measurements of their velocity and trajectory have suggested something quite different. The Magellanic Clouds may be traveling too fast to have been in close orbit around the Milky Way for long. Their speed hints that this may, in fact, be their first close approach, that they are newcomers, Cosmic visitors, galaxies that have spent most of their existence drifting independently through intergalactic space and are only now, for the first time, falling under the Milky Way's influence. If true, they are not ancient companions. They are strangers arriving for the first time. Distant wanderers whose trajectories have finally curved toward our galaxy, drawn in by gravity for the first encounter. Their arrival has already left its mark. The outer disk of the Milky Way is warped and distorted in ways that may be partly their doing, gravitational guests stirring the edge of our galaxy simply by their proximity. And trailing behind them across the southern sky is a vast ribbon of stripped hydrogen gas, the Magellanic Stream, pulled away by tidal forces during their approach, stretching over hundreds of thousands of light-years, invisible in ordinary light but glowing in radio wavelengths. A long, trailing whisper of their passage through our neighborhood. Zoom out far enough from the Milky Way, far enough that the local group becomes a tiny cluster of faint lights, and something extraordinary comes into view. The universe is not smooth. On the very largest scales, hundreds of millions of light-years, matter in the universe is arranged in a breathtaking structure. Long filaments of galaxy clusters, stretching across hundreds of millions of light-years. Where filaments intersect, enormous superclusters accumulate, among the most massive gravitationally bound structures in the observable universe. Between the filaments, vast, nearly empty regions called cosmic voids, bubbles of space where almost nothing exists. The whole thing is called the cosmic web. And seen in 3 dimensions, it looks hauntingly like neurons in a brain, or like the mycelial network of a fungus, or like the structure of the internet, or like the vein pattern of a leaf. The same geometry emerging at completely different scales, for reasons that may be more than coincidental. The Milky Way sits in the local group. The local group sits within a larger structure called the Virgo supercluster, a region containing dozens of galaxy groups and clusters spanning about 500 million light-years. The Virgo supercluster is itself just one lobe of an even larger structure called the Laniakea supercluster, a gravitationally connected region containing approximately 100,000 galaxies and spanning 500 million light-years. The Milky Way. The local group. The Virgo supercluster. Laniakea. The cosmic web. Each one a layer of the same extraordinary structure, nested within each other like the rings of an immense, incomprehensible onion. And at the smallest layer of all, one ordinary star, in one ordinary spiral arm, on one small planet, in one quiet room, you are resting. Taking part in something much larger than any story ever told about it. Somewhere far across the universe, perhaps millions of light-years away, perhaps billions, 2 massive objects are spiraling toward each other. 2 black holes, perhaps. Or 2 neutron stars. Objects so massive that their mutual orbit distorts the fabric of space-time around them, sending ripples outward at the speed of light in every direction. These ripples are called gravitational waves. Einstein predicted their existence in 1916, as a consequence of his general theory of relativity. Space-time, he proposed, is not a fixed, rigid backdrop but a dynamic, flexible fabric that can be distorted by mass and energy, and when massive objects accelerate, they disturb that fabric, and the disturbance propagates outward as a wave. For decades, this was theory only. Gravitational waves were expected to be unimaginably tiny by the time they reached Earth from distant sources, compressing space by a fraction of a proton's width across a detector kilometers long. Surely too small to ever measure. On September 14, 2015, the LIGO Gravitational Wave Observatory detected a signal that had been traveling for approximately 1.3 billion years. 2 black holes, each more than 20 times the mass of the Sun, had spiraled together and merged. In the final fraction of a second of that merger, they released more energy in gravitational waves than the combined light output of all the stars in the observable universe. LIGO measured the distortion. Since then, dozens more detections have followed: black hole mergers, neutron-star collisions, events across billions of light-years of space, each one a new signal from the universe's most violent processes. A new kind of astronomy, gravitational wave astronomy, has opened, allowing us to observe the cosmos in a way that was impossible before. Even now, as you rest, as your breathing slows and the room is quiet, gravitational waves from somewhere in the universe are passing through this room. Through the walls, through you, through the planet itself. Distorting space by an amount so small it is undetectable without instruments designed specifically to catch it, but real. Space-time flexing as the information of an ancient collision finally arrives here, billions of years after the event that created it. The universe is not silent. It is full of waves. We are only just beginning to learn how to listen. You've heard of the habitable zone around a star, the region at the right distance for liquid water to exist on a planet's surface. Not too hot, not too cold. The Goldilocks zone. Astronomers have proposed that something analogous may exist at the galactic scale. A galactic habitable zone, a region of the Milky Way where conditions are favorable enough for complex life to develop and persist. Near the galactic center, conditions are extreme. The supermassive black hole exerts powerful gravitational influence. Massive stars are packed densely, exploding frequently as supernovas and bathing the surrounding space in intense radiation. The density of stars creates frequent gravitational encounters that might destabilize planetary orbits. Life, if it arises in this region, may face constant disruption before it has a chance to grow complex. In the outermost reaches of the disk, conditions are more peaceful, but there are fewer of the heavy elements that planets and life require. Carbon, oxygen, iron, phosphorus, these elements become less abundant farther from the center, where fewer generations of stars have lived and died to enrich the interstellar medium. Planets may be harder to form, and when they do, they may lack the raw materials biology needs. In between, at intermediate distances from the center, in a wide annular band running through the disk, conditions may be just right. Enough heavy elements for planets and chemistry. Enough distance from the core to reduce radiation and gravitational disruption. Enough stability for billions of years of continuous evolution. Earth lies within this zone. Our position in the Orion Spur, at a moderate distance from the galactic center, in a relatively quiet region between major spiral arms, it may not be coincidence. It may be exactly the location where life had the stability it needed to go from single-celled organisms to everything that exists today. We may not be at the center of the galaxy, but we may be in exactly the right place. Here is something about our solar system's journey through the galaxy that is surprisingly charming, if you let it be. As the Sun orbits the Milky Way, it doesn't travel in a perfectly flat line. It wobbles. It sways. It oscillates gently above and below the plane of the galactic disk, rising upward over tens of millions of years, crossing through the mid-plane, descending below it, then rising again. Like a cork floating in a slow, enormous, invisible wave. Like a small boat rising on a swell that takes 60 or 70 million years to pass. The cause is the gravitational influence of the galactic disk's mass. As the Sun moves slightly above the plane, the collective gravity of the disk below it pulls it back down. It overshoots, crosses through, rises on the other side, and is pulled back again. An endless, gentle oscillation across the thickness of the disk. Some researchers have speculated, and this remains uncertain, controversial, and not yet proven, that these crossings of the galactic plane might correlate with cycles of comet bombardment on Earth, as the Sun passes through denser regions of the disk where gravitational perturbations might disturb the outer solar system. If true, the extinction events in Earth's history might carry a faint cosmic rhythm, a galactic heartbeat measured in millions of years. The evidence is not clear. The connection is not established. But the question itself is extraordinary. Even on its steady, quiet orbit around the center of the galaxy, the Sun is not gliding. It is swaying. Softly, slowly, over timescales that dwarf human history, but swaying nonetheless, through a galaxy that does nothing quite perfectly and nothing quite still. Our solar system does not live in one of the Milky Way's grand major spiral arms. It lives in a smaller, quieter structure nestled between them, a region called the Orion Spur, or sometimes the local arm. The Orion Spur is not especially dense with stars. It is not a region of particularly intense star formation, nor does it host any especially dramatic ongoing astronomical events. By galactic standards, it is a quiet backwater, a calm lane of stars between the more active Sagittarius arm inward and the Perseus arm outward. And that quietness may be among the most important facts about where we live. In the major spiral arms, massive star formation is more common. Supernovas are more frequent. Radiation levels are higher. Gravitational disturbances from the density of nearby star systems are more intense. These are not conditions that favor the long, slow, stable process of biological evolution. Out here, in the Orion Spur, in this calm gap between the grand galactic highways, massive supernovas are rarer. Radiation storms less frequent. The solar system has been able to orbit for 4.5 billion years without significant disruption from our stellar neighborhood. Earth has had the time it needed. From the grandest vantage points, the galaxy seems dramatic and radiant, a cosmic spectacle of light and violence and transformation. But in this quiet spur, in this unremarkable corner between the arms, the conditions were just right. Just calm enough. Just long enough. For complexity to unfold, for life to emerge, for consciousness to wake up and begin asking where it was. Let's come back, slowly, from the grand scale of the galaxy and the cosmic web and the billions of years, and come back to you. Here. Now. In this room. Resting. The atoms that make up your body were not made on Earth. Earth itself formed from material that condensed from a cloud of gas and dust 4.5 billion years ago. But that cloud was already enriched. It was composed of atoms that had been forged elsewhere, in older stars, by older processes, and scattered into space by their deaths. The hydrogen atoms in your body, and hydrogen is abundant in every molecule of water, in every organic compound, were made in the Big Bang itself. Nearly 14 billion years ago. Before stars. Before galaxies. Before the cosmic web had any shape at all. The carbon in every molecule of your DNA was forged in the core of a red giant star that lived and died before our sun existed. The oxygen in your lungs was created in the burning cores of massive stars, scattered by their supernova explosions. The calcium in your bones, the iron carrying oxygen through your blood, the phosphorus at the center of the ATP molecules powering every cell in your body right now, all made in stars. All scattered by stellar deaths. All incorporated into the gas cloud that became our solar system. All eventually, through processes that took billions of years, becoming you. You are not made of matter that happened to come from stars. You are made of star matter. The Milky Way did not just give you a home. It gave you a body. It gave you the atoms to think with, to breathe with, to feel with. The iron now carrying oxygen to your brain, the brain that is, gently, drifting toward sleep, was forged in the explosion of a star that died billions of years before the Earth existed. You are not separate from the galaxy. You are an expression of it. Even with the most powerful instruments ever built, the Hubble Space Telescope, the James Webb Space Telescope, the Gaia mission, radio telescope array spanning continents, gravitational wave detectors sensitive enough to measure a distortion 1,000th the width of a proton, we have glimpsed only a fraction of what the Milky Way contains. We do not know exactly how many planets the galaxy contains. Current estimates based on statistical analysis of exoplanet surveys suggest hundreds of billions, perhaps more planets than stars, but we have directly confirmed only a few thousand. We do not know the full extent of the dark matter halo. We do not know whether it harbors its own structures. We do not know what dark matter actually is. We do not know how many rogue planets drift through the galaxy, nameless and lightless, beyond any telescope's reach. We do not know whether any of the 100 billion or more planetary systems in the Milky Way harbor life. We do not know if we are alone. The galaxy is large enough, and old enough, and chemically complex enough, that the ingredients for life appear to be common. But whether those ingredients have come together elsewhere into something that thinks and wonders, we don't know. The Milky Way is not just what we see. It is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that immensity, somehow, impossibly, we find ourselves. Small and temporary, yes. But aware. Curious. Resting at the edge of sleep, still asking where we are. And now, the stars begin to dim behind your thoughts. We have traveled a long way together tonight. From the outermost halo stars, ancient wanderers drifting in tilted orbits, older than the galaxy they now inhabit, all the way to the turbulent, sleeping heart of the Milky Way, where for millions solar masses of compressed gravity waits in the dark. We have watched stars being born in cold molecular clouds, in the slow, patient collapse of gas that has been wandering through the spiral arms for millions of years. We have watched them live, fusing hydrogen into helium, helium into carbon, carbon into oxygen and silicon and iron, in cores of unimaginable heat and density. We have watched them die. Some gently, drifting their outer layers into space as luminous planetary nebulae. Others violently, in supernovas that forged the elements now in your blood and your bones, scattered them into the galaxy, and gave the next generation of stars and planets the raw material they needed. We have drifted past rogue stars hurtling into intergalactic space. Past rogue planets drifting in permanent darkness. Past stellar streams, the ghostly remnants of galaxies the Milky Way consumed billions of years ago, their stars now tracing long, looping arcs through the halo, carrying forward the memory of worlds that no longer exist. We have heard the galaxy breathe, the slow circulation of gas from disk to halo and back again, the galactic fountain cycling material across millions of years. We have felt, in the only way available to us, the invisible magnetic field threading through the bones of the spiral. The cosmic rays streaming through this room. The neutrinos passing through you, right now, from the fires of the Milky Way. And we have come home. To the Orion Spur. To this quiet corner of the galaxy between the great spiral arms. To one star among 100 billion. To one planet among hundreds of billions. To one continent, one country, one city, one room, one resting body. You are part of this galaxy. Not just a passenger on Earth, a participant in its long and luminous unfolding. The iron in your blood was forged in ancient stars. The oxygen in your lungs was sculpted in stellar explosions. The atoms of your body trace their lineage to the very first moments of the universe, born from the same matter that now fuels suns 100,000 light-years from here. Tonight, as you rest, the galaxy turns on. Stars are forming in cold molecular clouds, gravity drawing wisps of gas together in the dark. Light is traveling, ancient light, from stars that may no longer exist, still moving through space, still crossing the void. Silent orbits continue, the Sun sweeping forward through its 21st galactic year, the Earth turning, the Moon circling, everything in motion without any sensation of speed. And you are floating within all of it. A small warmth in the dark. Resting in the spiral arm of a quiet, radiant, ancient, still growing, still surprising galaxy. Thank you for spending tonight here on the Sleepy Analyst. If you're still awake, if the words are still finding you at the surface, you can let them go now. Let the images drift. Let the scale of it all do what scale does best, remind you that your worries, as real as they are, exist inside something immeasurably larger and older and quieter than anything that troubled you today. Sleep well. Dream softly. Good night.